evaluate the velocity. Okay, so this question is like a problem, so we are treating this question like a problem. So we are going to solve what is the velocity that is induced by vorticity. So there are two ways in which you can interpret this. There is a velocity that may be induced by vorticity, or the other way is that there is a velocity field exists, which velocity field's curl will give you the specified or prescribed vorticity. Okay. So sometimes there is a cause and effect kind of thought process in our heads that okay, vorticity is existing, that is causing this velocity to exist like this. No, that's not correct. Both vorticity and velocity exist simultaneously, and we are trying to we are trying to go the other way or the reverse way in finding velocity which will make up that prescribed vorticity. Okay, the reason why I use the word induced is because it is easier to visualize it as a velocity that is induced by vorticity, but there is no cause effect here. Okay, they both exist simultaneously. Okay, so the question is, let us say you have, so given a vorticity field in infinite domain. So in infinite domain meaning, so we have vorticity given in the whole real space. Now of course there is no fluid problems, there is no fluid flow that exists in a truly infinite space. Okay, there's some bounds in reality always, but the physical significance of using an infinite domain is, let us say you are trying to analyze flow in a very small domain, but the boundaries are very far away. Okay, so this brings up the concept of length scales as well, that the length scale at which the boundaries exist are way larger than the length scales of the flow. In that case, you can approximate your problem as a problem in an infinite domain. Okay, when you are very far away from all boundaries in all three directions, in that case you can approximate your problem as a problem in an infinite domain. So whenever I write it like this, physically you should think about given vorticity in some domain which and the whole domain is very far away from any physical boundaries. Okay, so given this, find u such that we have del cross u equals omega. Okay. Now to do this, we use the Helmholtz decomposition. So Helmholtz decomposition says that for any vector field, so if you are given any vector field which for us is the velocity, then I can write it as gradient of a scalar field plus curl of a vector field. Usually this phi is called the scalar potential or just potential, scalar potential of velocity field, and this A is called the vector potential. Okay, I am not going to prove why this can be done. You can look at basic maths, vector calculus textbooks to confirm. So for this course, we are just going to accept that this kind of a decomposition exists, and we are going to develop further. Okay. So now let us say I give you this equation and ask you, can you find unique phi or unique A fields just given this information? Is it possible to find unique functions for phi or A just given this equation? Is it possible to find unique phi or unique A just given this equation? Heads are shaking no, why not? Why can't I find unique phi or unique A just given this equation? Those who were saying no, they can try and answer. Can I find unique phi or unique A just given this equation? No idea. So this is a differential equation in phi or A. I am not giving you any boundary conditions or anything. Okay. right. So, we cannot find a unique function, but it is not just a constant that I add. Let us say I formulate an a tilde and I add some value like this to a tilde. In this case also you will see that del cross a tilde by definition is actually equal to del cross a. Okay. So, we cannot find these functions uniquely, not just because we can add any scalar. So, we can add any scalar function to phi, okay, but we can actually add any we can add any function phi tilde or grad of phi tilde. So, I can add any. So, you can look at this as some function f, vector function f. I can add any vector valued function f to a, which can be written like a gradient of a scalar function, and even in that case the velocity will not change. Okay. So, this means that this a is defined up to an arbitrary, this a is defined up to an arbitrary grad phi tilde. That is, I could add any function which can be written as a gradient of a scalar function and add it to a, formulate an a tilde, it will not affect my velocity. Okay. So, there is a degree of freedom in choosing this a. Okay. So, what we choose is whenever we have this kind of a arbitrariness, we can make a choice. So, we make a choice that okay, I am going to require that my del dot a is equal to 0. Okay. I am going to choose an a such that del dot a is going to be 0. This is my choice. The moment I make this choice, look what happens. So, the moment I make this choice, this del cross A, okay, let us take a cross product of this equation. You have del cross u, so then we have del cross grad phi plus del cross A. So, this is omega. What is this by definition? Del cross grad phi. What is this by definition? 0. And then we have this. So, you can open this up using your index notation and you will find that this is nothing but del of del dot A minus del square A. Okay, and I am choosing this A such that this guy is 0. So, that means omega equals minus del square of A. So, if I can solve this equation, if I can solve omega equals minus del square A, if I can solve omega equals minus del square A, I can solve for A, let us say using this equation, then I can plug that A here and I can find the velocity which will give me this vorticity, the prescribed vorticity. Given this vorticity, I can find the velocity field which will result in that vorticity. Okay. So, that is what our problem becomes when we are posed this question that okay, you want to solve this equation to find that velocity. So, this equation is in whole 3D space, let us say whole 3D space or infinite domain, whatever you want to call it. Okay. Usually in maths this is denoted by this real space in 3D, okay, the whole real space in 3D. So, if you were to write an integration using Cartesian coordinates x y z, all x y z will vary from minus infinity to infinity, okay, that is what this means. So, we want to solve this equation, okay, we want to solve this equation. So, we want to solve basically this is your Poisson's equation in, we want to solve this guy. Okay. And a standard technique for solving these kind of equations is, have you guys covered Green's functions in any courses, in any of your courses? So, standard technique of solving this is using Green's function. So, the Green's function is a very powerful tool to solve these kind of equations, to solve particularly inhomogeneous equations. So, this is an inhomogeneous equation, okay. There is a Poisson equation, this is an inhomogeneous equation. This is very similar to what we had to solve for flow through pipes, okay. But there we had to solve this in a bounded domain. We were solving this equation in a bounded domain. Now we are solving it in an unbounded domain, okay. So, we can use this Green's function. We can use Green's function when we have bounded domains also, but you have to construct those Green's functions, which is very tedious. So, we are not going to bother with that. We are just going to solve using Green's function in the infinite domain. Okay. So, first what is Green's function? Green's function is defined. So, this g function is defined such that del square of g is actually delta of x minus y, where g is a function of x and y vectors, where y is another point in 3D space. Okay. So, this is like x point and this is like y point. The physical intuition of g is that what you should think of this equation as is, let us say you want to calculate a at a point x. What you are going to do is, okay, if I had a Dirac, so this is Dirac delta, by the way, I will give a definition of this. This is Dirac delta, and what we are trying to say is, okay, this omega function, let us say it was Dirac delta, let us say it had some value only at a single point and it was 0 everywhere. What is the effect of that on x? And then what we are going to do is we are going to integrate the effect of all such y's on an x to find the value of this a on that x. Okay, that is the physical intuition of what is going on when we use Green's function for solving these equations. Okay. So, what we are going to do here is, first let me give a definition of this Dirac delta. So, Dirac delta in 1D is defined as, so delta of x minus y is actually defined as 1 by 2 pi minus infinity to infinity e to the power I k x minus y d k. Okay. So, you can think about Dirac delta like this, and Dirac delta has properties. The first property of Dirac delta is that this guy is equal to 1. Okay. Integration of Dirac delta over the whole line or over the whole infinite domain is 1, and the second property of Dirac delta is that f of y delta y minus x dy is actually equal to f of x. For any function, I can multiply it with Dirac delta y minus x, integrate over all y's, then the function's value will only survive for that value where delta is non-zero. Okay. To visualize Dirac delta, you can think about Dirac delta. Let us say this is your point x naught, then delta of x minus x naught will look like this. It is 0 everywhere, shoots up to almost infinity at x naught and 0 everywhere else. Okay. So, these are the this is how Dirac delta is defined for our course. So, there are multiple definitions or representations of Dirac delta, but we are going to use this for now. So, in 3D this is defined as x and y are vectors now, and this is defined as all 3 minus infinity to infinity e to the power I k wave vector or k vector x minus y with a dot product here, and then you have a dk. So, this dk essentially is the volume element. Okay. So, dk 1 times dk 2 times dk 3, that is how I am writing this dk. Okay, this is the definition of my Dirac delta in 3D, and that is what I am going to put here. Okay, for those of you who are curious, you can quickly see the similarity between the definition of Dirac delta and how we have defined our Fourier transform and inverse Fourier transform pairs. Okay, so you can think about what exactly is the Dirac delta inverse Fourier transform of. Okay. So these guys in 3D, they have a 3D counterpart as well. So when your f of x, where x is in 3D 3-dimensional domain, we have 3D counterparts of Fourier transforms as well. And then these pairs, Fourier and inverse Fourier, they exist like this. Okay. So now what we are going to do is we are going to solve for this Green's function, and what I am going to do is I am going to solve for the Green's function, I am going to take Fourier transform on both the sides. Okay. So I want to know what is the Fourier transform of del square g. So first let me write g. So the Fourier transform is happening, or everything is happening in x direction, in x vector. Okay. All of these things are happening in x. So we have g hat k e to the power I k dot x dk. And then if I want to calculate del square, I basically want to calculate del square of this or Laplacian of this. So since this integration is over k, this differentiation is with respect to this x. So I can take this inside, and what will I get? What will I get? This will be minus infinity to infinity g hat k del square of e to the power I k dot x dk. So what do we get here? Del square of e to the power I k dot x. Minus, what is k square? Basically mod of k. Huh? So that is basically del square g is minus k square g hat. Let's write minus here, e to the power I k dot x dk. So that means the Fourier transform of del square g is simply minus k square g hat. Okay. What is the Fourier transform of delta x minus y? If you just look at this expression or look at these two expressions, this and this. So what is the Fourier transform of delta x minus y? What is the Fourier transform of delta x minus y? Just look at that expression. Actually, just give me I think I made a mistake. I think this 2 pi was supposed to be here. Where did we put the 2 pi in our last lecture? Can you just go to your notes and confirm? Did we put it in the Fourier transform definition or inverse Fourier transform definition? I just want to keep this consistent. Where did we define that? Where did we keep the 2 pi? Huh? So here, when I am evaluating f of x using Fourier transform. Okay, so please make this correction. I had written the formulas also. They don't, as I said, they don't make any difference. They can be defined with replacing 1 by 2 pi instead of here, but you have to keep everything consistent. So just to keep this consistency, I am going to, please make this correction in the notes. Okay. So now if you compare this and this, So we'll need a 1 by 8 pi cube will come here as well, no? 1 by 8 pi cube. So we'll have this as 1 by 8 pi cube. So what is the Fourier transform of delta x minus y? If you just look at this expression, if I use instead of f hat k, I use e to the power minus k dot y, then I will get this equation, right? If I use f hat, I choose f hat as e to the power minus I k dot y, then I will get this. So the Fourier transform of delta x minus y is simply e to the power minus I k dot y. Okay. So we have this as g hat. G hat is simply e to the power minus I k dot y over k square with a minus sign. So that means we can calculate our g by now substituting it here. This is integration 1 by 8 pi cube minus infinity to infinity e to the power I minus I k dot y by k square. There is a minus sign also here. So this times e to the power I k dot x dk. So this is minus 1 by 8 pi cube okay. So now we are going to use the change of variables to evaluate this integral. Okay. We can use the change of variables to evaluate the integral such that so you have e to the power I k dot x minus y. So what we are going to do is, let us say this is your k vector, anywhere this is a k vector and this is your x minus y vector. Okay. So what I am going to do is, instead of writing this in Cartesian coordinates, I am going to do this in spherical coordinates. Okay. I am going to do this in spherical coordinates. How? So let us say this is your k vector, the angle that it is making with x minus y is theta. Okay. So the we have to span the whole 3D space using this. So what this angle will go from, let us say this angle will go from 0 to pi, okay, and then I rotate it over whole 2 pi ring. So I make a 2 pi ring, okay. I vary this angle from 0 to pi. I vary this over the whole 2 pi length and I vary k from 0 to infinity. So the integration limits will change. Let us say the angle that goes from 0 to 2 pi is phi. So that goes from 0 to 2 pi. This angle goes from 0 to pi and then k goes from 0 to infinity. So in this case this will be e to the power I k mod x minus y cos theta, the dot product. This k without any notation is basically mod of k. Okay. This is what you get divided by k square, and now we have to look at what is our volume element. What is the volume element in spherical coordinates? How do we get the volume element in spherical coordinates? What is it? No, that's polar coordinates. This is spherical coordinates. So over a sphere, let us say over a sphere, how do you get the volume element? So the radius of this ring is what? So let us say this is your r, this is your angle theta that is varying from 0 to 2 pi. The radius of this ring is r sin theta. Okay, r sin theta times d phi is the length. Okay, that times r d theta is this length, and that times the thickness of the element, you get dr. So this is how you write your volume element in spherical coordinates. Okay, so first it's like you have a sphere, you make a ring, you have r d theta, r sine theta d phi, and then dr is the thickness. So this dk has to be written like k square sine theta d theta d phi dk. These are the limits of phi and these are the limits of theta. Okay, you can solve this integral, you should be able to solve this integral. You should be able to solve this integral. So phi there is no variation, k square cancels out. Okay, so phi just gives you a 2 pi in front. There's no, this is not a function of phi, except for d phi there is no phi appearing, so you get a 2 pi, and then you get theta varies from 0 to pi and k varies from 0 to infinity e to the power I k mod x minus y cos theta sin theta d theta times dk. You can write it like this.
Could you explain how did you convert the x minus y and k to the spherical coordinates?
So what I am doing is this k is a vector, x minus y is a vector. Okay, I am defining the space using spherical coordinates where this angle theta is with respect to x minus y vector. You can always do that, no? So k dot x minus y is what? Mod k mod x minus y cos theta. Okay, so that is how I am defining this k dot x minus y. You can substitute here cos theta, you can make the substitution, you can evaluate this integral. Okay, eventually I'll just write the result here, and the result that comes out is, so when you are solving this equation, the result that comes out is that g of x comma y is actually equal to I think there's a minus here, so minus 1 by 4 pi, sorry, no integral, minus 1 by 4 pi mod x minus y. This is the final result that you should be able to get after simplifying this integral. Okay, I am not going to do the steps of this integration because we have more things to cover, and these things are basically, I mean, I am going into, or I am offsetting the lack of education in PDEs and Fourier transforms for you guys. So this is technically, as you can all obviously expect, this is all mathematics course. So technically I should not be needing to cover this, but since you guys don't know Green's function, I am having to cover this. So the idea is, once you have this g of x comma y, you can solve this equation. Let's say you are given an equation del square f equals g small g. You can solve this equation how? You can write that your f is actually equal to integral of g of x comma y small g of y dy. Okay, and the integration should be over the whole 3D space. This is again, this is, I don't know if you guys have done any courses in vibration or something, but when you have forced vibration of a system, let's say a spring mass damper system, this is the standard way on in how you evaluate the solution. Yeah.
I want to confirm that you've assumed even k as the Fourier transform of gx comma y.
What?
So we started off by assuming even hat k as the Fourier
E1
transform.
hat k?
Is that even hat g? G hat.
अरे अरे ये तो गड़बड़ हो गई, ये तो
That's g, right?
या तो रामायण खत्म हो गई तो तुम पूछ रहे हो सीता
नहीं मैं
किसका बाप था.
कंफर्म कर रहा था वो राइट में. That's why I was getting confused कि even लग रहा था मेरे को.
Sorry for my handwriting. This is G. This is no, there is no nowhere I have written even so far. Okay. I have not written E1 anywhere. This is G. This is how I write my G. Okay, so this is how we can evaluate the solution of this equation, given that this is defined over the whole 3D space. Okay, if you have bounded domain, you have boundary conditions, and then G takes a very different form and the solution takes a very different form. We're not going to bother that.
F is a scalar function.
Yeah, so it can be a vector function as well. So if I have this, then this is just this. Okay, there is really no difference. So from here you see that your A becomes, so what does your A become? If I want to solve this equation, your A becomes, so you have two minus signs, so they will cancel out and you will be left with this integral. Okay, this is what your A will be given an omega. This is what your vector potential will be given the vorticity omega. This is what my vector potential is given vorticity omega, and now we can calculate the velocity induced by this omega as del cross A, and that is 1 by 4 pi r cube del cross omega by mod x minus y dy. Okay, this not del cross omega, sorry, del cross of this whole thing, and this differentiation is in x direction. Okay, is in with respect to x point. So y point is your integration point. Everything is a function of x eventually. This guy is a function of x. Okay, here A you get as a function of x, not y. So just be careful with that. You are integrating y out. You are integrating it over the whole r cube. So if you want to calculate this del cross omega, okay, so this is del cross omega. So let's simplify this. I want to calculate del cross, not del cross omega, del cross omega over mod x minus y. So this omega is a function of y actually, right? This omega is a function of y. So essentially what we are looking for is omega times del cross 1 by mod x minus y. Okay, so this del cross mod 1 by mod x minus y we can actually calculate using index notation. So this is going to be a vector. It is epsilon I j k del by del x j, and then just a second. Yeah, let us write not like this, because 1 by mod x minus y is not a vector, right? So let us just write like this, and then omega is my vector. So del by del x j of omega k by mod x minus y. Okay, and then so this is your epsilon I j k. So the vector is e hat I. How do we simplify this? So omega k is not a function of x. So we can bring it out. So you have omega k epsilon I j k del by del x j 1 by mod x minus y e hat I. How do we calculate del by del x j? 1 by mod x minus y. How do we calculate this? How are we going to calculate this? So this is nothing but minus 1 by mod x minus y square del of mod x minus y by del xj, and this you guys can calculate. Okay, del of mod x minus y by del xj you can calculate how. So x minus y, so this x and y, these are all vectors. Okay, so mod x minus y dot mod x minus y, oh sorry, x minus is, this is square. You can differentiate this with respect to xj, so you can write it like, okay, differentiate the whole equation, and this is basically x, this is x minus y kth component times x minus y kth component and del by del xj of that. Okay, and 2 mod x minus y del mod x minus y by del xj. Okay, so you can differentiate this, you will get 2 times xk minus yk times this guy, which is basically delta kj, equals 2 mod x minus y del mod x minus y over del xj. And then this becomes xj minus yj. So, the derivative, this derivative is essentially the unit vector, this derivative del x minus y by del xj is essentially the unit vector in the direction of x minus y vector. Okay, this is what you get from here. So, del x minus y by del xj becomes xj minus yj by its magnitude, which is the unit vector pointing in the, pointing from x to y. Just a couple of steps of algebra more, and then we will reach an equation which is very intuitive. I mean, we had to do this, all of this algebra to reach a result, and that result is very intuitive actually. Okay. So, you have this del by del xj of 1 by mod x minus y as, and then this guy, which is nothing but xj minus yj over mod x minus y. So, this is nothing but x minus y vector over mod x minus y cube with a minus sign. Okay. So, let us substitute that here, which is what we were trying to evaluate. So, we have epsilon I j k omega k and then a minus of x j minus y j over mod x minus y cube, which is a scalar, and then an e hat I. This is nothing but, so epsilon I j k omega k x j minus y j. What is that? That is x minus y vector cross omega vector by mod x minus y cube with a minus sign. So, if you have a cross b and a minus sign, so you can write it as omega cross x minus y over mod x minus y whole cube. So, this expression, this del cross of omega y by mod x minus y gives us this, and now we reach the result, and the result is that del cross A is equal to 1 by 4 pi r cube omega cross x minus y over mod x minus y cube dy. Now, the reason why I say this is a very intuitive result is because, let us say you have vorticity, let us say you have vorticity on a point y. So, this is your point y, you have vorticity which looks like, so vorticity gives the direction of rotation to the fluid in this sense. Okay. So, let us say you have vorticity and it gives the direction of rotation to the fluid in this sense. Now, I am asking you, okay, what is the velocity at x point due to this vorticity. Okay, again I am using the word due to vorticity, but keep in mind that both of them exist simultaneously. So, if you have this kind of a situation, then what would you expect the velocity direction to be? So, this is omega cross x minus y. So, if your omega is coming out of the board, your omega is coming out of the board, okay, x minus y is this vector. So, no, sorry, omega is going inside the board, not out of the board. Omega is going inside the board, omega is going inside the board, x minus y is this vector. So, you expect that the velocity is going to be like this, very intuitive. Okay. This is what your omega cross x minus y is giving you. Okay. So, if you have, let us say, if I give you a situation where I tell you that okay, there are two vortices which exist like this, they have this kind of a sense of rotation. There are two vortices which exist like this. Okay. Then this guy will be making this one move down and this guy will be making this one move down. So, the moment you have two vortices, due to their induced velocity or due to each other's induced velocity, they will be moving down. And now we can extend this into a vortex ring. Okay. Let us say you have a vortex ring. I had this. Okay. So, let us say you have a vortex ring and the sense of rotation of vortex ring is such that it is always from outside to inside. Okay. From outside to inside, this is the sense of rotation. Then due to this, due to the vorticity here, this point will move in this direction inside the board. Due to vorticity here, this point will move in this direction, and all diametrically opposite points essentially are making the point move in a single direction. So, by virtue of its existence, this vortex ring will propagate, it will move. You cannot have a stationary vortex ring. Simply because you have a vortex ring, this vortex, the vorticity here is going to move it here, this vorticity is going to move this point here. So, all the points are going to move their diametrically opposite point in a direction, in a single direction. So, the whole vortex ring as it is will move. Okay. So, vortex rings are not stationary, they move, and you can compute the velocity, you can compute the fluid velocity using this expression. So, all of this algebra we had to do just to answer the question, what is the velocity del cross A, what is this velocity given a vorticity, what velocity will cause a vorticity that is prescribed. Okay. We have answered that question. So, we have calculated del cross A and this is what del cross A is supposed to be. Any questions? So, all of this is actually given in the kinematics chapter, okay, because it makes sense to keep it there. The reason why I discuss it while discussing the solutions is because we are in the zone of discussing Fourier series, Fourier transform, separation of variables. So, it makes more sense there, but all of this is actually given in the kinematics chapter because it makes sense. This is kinematics. Okay, this is basically answering the question. Okay, we had defined vorticity. So, I had defined omega is del cross u. So, a straightforward extension is okay. If I give omega, can you calculate u? So, it is really a part of kinematics, but for this course it makes sense to discuss it here. Okay. So, if there are no questions, then we will proceed and we will look at the last problem in this chapter. I mean last problem which we are going to discuss in the class. There are many problems which we can formulate, and the last problem which makes sense to be discussed, and that is the problem of Stokes oscillating plate. And this is a very similar problem to Rayleigh's problem, where you had an impulsively moving plate with a constant speed u naught. This problem is that you have an semi infinite domain. So, the fluid is extending from y equal to 0 to y equal to y tends to infinity, and then the plate that you have at the bottom, it is not actually impulsively moving, it is oscillating, and the oscillating velocity is, let us say, u cos omega t, where this omega is the frequency of oscillation of the plate. This is a very similar problem uh, to your standard spring mass damper system, which is forced. Have you guys done those in any courses? You guys have done dynamical systems in those courses, right? Have you done this problem basically? So, let us say you have this is m, you have f, which is f naught e to the power I omega t, k, this is c. So, the governing equation for this is mx double dot plus kx plus cx dot equals f. And so, what is the usual way of solving this? How do we solve this equation? When your force is harmonically varying, when your force is oscillating, then how do we solve this?
First find out the homogeneous solution.
Okay, sure. Let us say I am not interested in homogeneous solution, but I am interested only in the particular solution. It is a good answer, because technically this is an inhomogeneous equation. So, there are two solutions, solution has two parts to it, one is a homogeneous, one is an inhomogeneous solution. How do we evaluate the inhomogeneous solution of this?
We assume x to be some function.
Like what?
Just different amplitude and frequency.
So, x you say is some x e to the power I omega t with the same frequency as this guy, right, and then you substitute it here, and then you find the amplitude. Okay. Essentially what you are doing is you are not assuming anything. Okay. Essentially you are not assuming anything, you are taking the Fourier transform of this whole equation, Fourier transform in time. If you take the Fourier transform of this whole equation in time, you will get exactly what you just said. Okay. So, the idea here is you assume that to be the solution. So, that is what we are going to follow here with all the assumptions that we have followed for Rayleigh's problem. So, similar assumptions as Rayleigh's problem. We obtain the equation del u by del t equals nu del 2u over del y square. But this time our boundary conditions are slightly different. Our boundary conditions are slightly different. Instead of the velocity being constant at y equal to 0, you have u at y equal to 0 for all times varying as u naught cos omega t, and u for y tends to infinity is 0. So, this part is slightly different, this part is same. Okay. And now an important point here is that what happens to the initial condition? What happens to the initial condition? Okay. There are two parts of this of the solution here, as your friend said, that there is a homogeneous solution and there is a particular solution. The particular solution is the steady state solution. This system, let us say it starts with rest, you start forcing it with an oscillating force. After some time you will find this mass oscillating with a constant frequency and constant amplitude. That is what I mean by steady state. But there is a transient also, there is a transient solution also, which starts from no displacement x equal to 0 and it reaches that. Okay. The transient is actually governed by your initial condition, but steady state solution actually is independent of your initial condition. Okay. As you will see just now, the thing is, if here also you assume that x is, let us say, real part of x e to the power I omega t, capital X e to the power I omega t, then you are forgetting about what is the initial condition here. You have already assumed that this solution is harmonically varying, it is varying with a constant frequency omega and a constant amplitude. Okay. So, the initial conditions actually will not play any role when we try to find this equation, find the solution of this equation at steady state. When we try to find it at in the transients, that is where we will use the initial condition. So, for example, if you look at this solution of this equation, if you plot x versus t, you get this type of a solution, okay, depending on if your system is over damped or under damped, you may get this type of a solution. This is what I am referring to as steady state, okay, and this is your transient. No matter where you start from, no matter where you start from, your steady state will be same, your transient will be different. Okay, that is the idea here. So, in our next class, we will calculate this both the steady state and transient solution of this problem.